So, Professor Saikia, we are going to start.
Yeah, we can start now.
So, good evening, everyone. Today, in our IEEE SBC chapter, here we are hosting IEEE talk that is we used to conduct every month normally. So today's topic is a talk on application of Steiner tree in 5G and 6G communication network. So good evening everyone to all the audience who are present and also Professor Parikshit Saikia. So first, I would like to give a short introduction about Dr. Parikshit Saikia. Then we'll have some general instructions. Then Parikshit Saikia can start the talk. So first, I would like to introduce our student chapter. That is name is IEEE CSSBC student branch chapter IIT Kharagpur. So, like today's topic is application of Steiner tree in 5G and 6G communication networks. So, I'd like to give a short introduction about Dr. Parikshit Saikia, who is our speaker. So, he's an assistant professor from NIT Silchar. So, his education details, he has done his PhD and MTech from Computer Science and Engineering Department from IIT Kharagpur, IIT Guwahati. Sorry. And he has done his BTech Bachelor's of Engineers from Assam Engineering College. And his work experience and achievements are like best paper. He has got best paper award in CNDR 2019 held at Nagasaki, Japan. And also previously he was an assistant professor in IIIT Pune, Birla Institute of Technology, Meshra, Ranchi, NIT Hamirpur, and Girijananda Chaudhary Institute of Management and Technology, Guwahati. So presently he is an assistant professor in the Department of Computer Science and Engineering, NIT Silchar. So his research interest mainly includes distributed computing, distributed artificial intelligence, graph algorithm, distributed approximation, and communication networks. So these are the very short introduction. So definitely anyone who are interested to see the details, they can explore Google Scholar directly. And here is the general instructions I'd like to say to all. So please keep your self muted during the talk, and also please wait till the end of the talk to ask.
Sorry for interruption, Kumar. Actually, your slide is not moving. Is there any slide?
Oh yes, sir. Yes, sir. Sorry, sir.
Now it's okay. Yes, now
okay.
It's moving.
So please, it's a general instructions to all. So please wait till end of the talk to ask any question. There will be a separate question and answer session at the end. And an attendance sheet will be distributed. Please note your attendance there. And also you may type any query or issues if you're facing in the chat box only. And also you'll be taking a group screenshot at the end of the event. And during that time, you can turn on your camera, and all the audience can turn on the camera. Okay, so sir, Dr. Saikia, I think now you can share your presentation and you can start your talk. Thank you, sir.
Yeah, thank you, Kumarjit, for a nice introduction about me. Yeah, let me share the screen first.
Yes, sir.
I think entire screen will be fine. Okay, let me see this one. Hello everyone, please confirm whether my PPT is visible to you or not.
Yes, sir. It's visible clearly.
Okay, great. Okay, let's start then. Hello everyone, my name is Dr. Parikshit Saikia. Already I'm introduced by Kamarjit Roy. And first of all, I would like to thank you, IEEE Computer Society Student Run Chapter IIT Kharagpur, for giving this opportunity to talk about our research topic. Basically, our research, today's topic is application of Steiner tree in communication network, specifically in the context of 5G, 6G. The talk will be mainly on this topic, Steiner tree, then application of this problem as well as a few use cases in communication network. So at the beginning, we will introduce about the problem. And then we will discuss about some of the fundamental models in distributed computing. Then one of the works we will discuss as a distributed Steiner tree algorithm, followed by some of the use cases or applications of Steiner tree. Okay. To begin with, the Steiner tree problem is a generalized problem of minimum spanning tree problem. I hope many of you have already heard about the problem called minimum spanning tree problem. So in minimum spanning tree problem, what the graph is given with a set of vertices, with a set of edges, and each edge is assigned with some edge weights, and we need to connect the set of vertices with minimum total edge weights, and we have to connect all the vertices. But what is Steiner tree problem is that in the Steiner tree problem, a subset of vertices are given, not all the vertices are required to connect. Okay. So formally we define the Steiner tree problem like this. So given connected, weighted and undirected graph and a subset of vertices which we call as a terminal set, we have to connect that given terminal set with minimum total edge weights. Okay, and if required, some of the additional vertices from the graph can be added or used. So if we see this problem is a generalized version of the minimum spanning tree problem, as we have already mentioned. And when we say only two vertices in the graph need to be connected, then the problem becomes finding shortest path between two distinct nodes. Okay? But as we are aware that the minimum spanning tree problem can be solved in polynomial time by using Prim's algorithm. But in general, the Steiner tree problem, it is a NP complete problem in terms of complexity class. So finding the optimal solution in polynomial time is not possible as per the complexity class. To understand what is the problem, you take one graph, a simple graph, consists of 6 vertices. Here black vertices are the vertices which we call it is a terminal vertex. And we need to connect these 3 terminal vertices with minimum total edge weights. Okay. So there are many possibilities. So one of the possibilities of connecting these three vertices is like this. Here the edges with red color, they are actually connecting these three vertices, but in addition, one vertex, which is the vertex B, it is also used to connect these three vertices. And the total cost of connecting this is actually 8. Similarly, another possibilities of connecting these three black vertices, and cost will be 7. So in this way, there will be many possibilities. There will be, we say, the exponential number of possibilities, out of which we have to find the one which gives the minimum cost of connecting these three vertices. So this is the Steiner tree problem. So you have to find the minimum total edge width connecting these two vertices. So here the some of the terminology we should know, that here black vertices again we call as the terminals, and white vertices which are included we call as a Steiner points or Steiner nodes. So Steiner, actually it is in the honor of Jacob Steiner. He studied this problem in the 18th century extensively. That's why in his honor the name is given as a Steiner tree problem. Okay, so this way we have to find the some tree which gives the minimum total edge widths. Hello, am I audible?
Yes, sir, it's clearly audible.
Okay, am I going fast, or someone should? Is it
No,
okay?
sir, it's very fine. Yes, sir, it's very okay.
Oh, okay. Thank you very much. So basically, in very generalized form, it has a lot of applications. Okay, in communication networks, it has application in VLSI layout design. It has application in computational biology. It has applications specifically for finding the phylogenetic tree. So details we are not going to discuss. And also this problem, Steiner tree problem, it is a sub-problem for many other problems like price collecting Steiner tree, Steiner forest, etc. Okay. Okay, but our focus of work mainly is in distributed setting, not the centralized setting. The problem of Steiner tree has been extensively studied in the sequential setting, or we also call a centralized setting, where whole graph or all the data is fed to a machine which is centralized, and we process it in single machine. That's what the centralized setting is. But in distributed setting, usually the whole graph, the graph usually we consider the number of nodes in terms of millions and number of edges in terms of millions. And so in such cases, sometimes getting such a huge data in a single machine may not be feasible. So and the world itself is in reality, world itself is distributed, so we go for distributed. And in distributed computing, specifically in theoretical aspects, there are three models: local model, congestion model, and congested gate model. Briefly, local model is that the links bandwidth between any two nodes in a network is considered as unbounded, means bandwidth is infinite. So this is the local model. In congestion model, this is a more realistic model where we always assume that congestion, there is a high probability of congestion, and that's why the links bandwidth is limited to some value. Specifically, the link bandwidth is order of log n, which where the n is the number of nodes in the network. And there is a special case of congestion model that is called congested gate model, and where we assume that each pair of vertices are directly connected to each other, and they can solve some problems by sending messages. Okay, so coming to how to solve the Steiner tree in distributed setting, towards this we propose one technique which computes a generalized minimum spanning tree. So ultimately the generalized minimum spanning tree is the Steiner tree. Okay, so we will see in a pictorial way about the algorithm, but before that, as we have already mentioned, that generalized MST is the Steiner tree. So for better understanding, I'm not going to give the formal definition of generalized MST, but here we can again see that a graph is given, the graph A, and 4 vertices colored with black. So these 4 vertices needs to be connected with minimum total edge widths. And in the right hand side, that is a figure, okay, it should be figure D, it is the corresponding generalized MST. And it is connecting these 4, I think 5 vertices, given vertices, black vertices here, and they uses 2 additional vertices which are white here. So this is the Steiner tree, which is the result of our algorithm, which will be the result of our proposed algorithm. So given the graph, we will compute this in distributed setting. Of course, our distributed setting, our distributed algorithm consists of all the model specification of distributed setting. It is a conjugate model, link bandwidth is limited, and it is a message passing. All those assumptions we assume in the ideal conditions, and we proposed, and our algorithm consists of 4 subroutines. We call it the subroutines, or 4 steps. The first step is the construction of the shortest path first. Second one is some edge weight modifications. Third one is the computation of the minimum spanning tree. The fourth one is some local optimization. So if we execute these 4 steps one after another, then it will produce the required resultant tree, which is the generalized minimum spanning tree, also the Steiner tree. Okay, for just to have a glance on how it works, consider a graph in figure 7. This is a graph. We need to connect these 4 black vertices with minimum total edge widths. The first step of our algorithm is to construct a shortest path first. Okay, basically there are shortest path trees, and this path tree is rotated at some terminal nodes. Here, for example, J, B, Z, R, these are the terminal nodes, and by considering the root of each of the shortest path tree, we construct a shortest path tree for each of such terminals. So, for example, the shortest path tree rooted at B is just A connecting to B. So with the colored edge, that is AB. Similarly, the shortest path tree for J consists of JH, JK, etc. Anyway, so it is a, first of all, forest. It consists of set of trees, and each trees are shortest path. That means how the nodes are connecting to the terminals. Suppose A, it can connect to J and also can connect to B, but since the distance from A to B is shortest, that's why it is joining the shortest path rooted at B. Similarly, all nodes are following that. So this is one step where we have to perform that. The first step is to compute the shortest path forest, and we have shown it in the order of n number of times. Okay. Then the next step is that since we have to perform the computation of minimum spanning tree, so some edge width modification is required, because already we have found some of the shortest paths. So those shortest paths are converted to some zero paths. Some edges which are not part of the shortest path, but their endpoints are in the same shortest path. In this case, those edges will form a cycle. So if it is a cycle, then it is not going to be a tree, because tree is always a cyclic graph. So these are some techniques we have applied. Just I'm giving us some hints. So that's how we modified the edges. Again, the modification of edges is also done in distributed way by using or sending messages among the nodes. Next, we apply the best known minimum spanning tree algorithm in the distributed setting. This is due to Gere-Kutet and Pelek algorithm. We call it as a Gere-Kutet and Pelek. And then finally, the pruning step is done. In the pruning step, for example, you can see that connecting J and B, A is no longer helpful for us. Similarly, connecting the J and G, because these nodes we are focusing to connect, not the other nodes, the black vertices. So for example, the subtree CDF consists of the vertices CDF, no longer helpful to connect any pair of terminals. So we can locally remove those set of vertices as well as edges. And this is called pruning. It's a local optimization technique. So finally we arrive this, and this is what the generalized MST, and in other terms, this is the Steiner tree. So basically, this computation is done in distributed setting by using message passing. Okay, some of the, it may not be so much important at this moment, but we achieve order of n times faster. Our algorithm is order of log n time faster than the base known. So base known is that this is a tilde order of capital S plus this terminology. Okay, due to the lack of time, we are not going to discuss in details, but we achieved order of log n times faster over the base known algorithm by using this technique. Okay, basically our major contribution in this proposed algorithm is finding the shortest path. Finding the shortest path, this is the major contribution where we achieved actually order of log n times first over the base known algorithms in literature. Okay, and yes, we have also proved it theoretically that the quality, the value of computed Steiner tree is not far from the optimal one by at most 2. So our computed value is at most 2 from the optimal. That means, in other words, we say the approximation factor achieved by our proposed algorithm is 2. At most it can compute twice of the optimal. Okay. So this is what about our introduction about the Steiner tree as well as our proposed algorithm. Coming to a generalized version of the Steiner tree itself. One is the Steiner tree itself is a generalized version of minimum spanning tree. Then price collecting Steiner tree is another generalized version of the Steiner tree. We will introduce this problem. What is the problem now? The graph is given, set of vertices are given, the set of edges are given, the edge weights are given. Each edge or links in the network is assigned with some value, either it is a distance value or hello. Is there any problem? Hello.
I think someone mistakenly turned on the mic.
Oh, okay. Thank you very much. Okay, so let's. So our problem is that a graph is given, set of vertices are given, set of vertices are connected by some links, and those links are also assigned with some values, maybe based on distance, and also each vertex assigned with some price value. This is the difference from the previous definition of the Steiner tree. So each vertex is assigned with some price value. So the goal of this problem is to find a tree where connecting the subset of vertices with some set of edges plus the set of vertices which are not included in the resultant tree, these two components should be minimum. So we have to minimize these two components. So for better understanding, so first part where the edge weights connecting the set of vertices, we call, this is called a Steiner part. The second part where the set of vertices will be not included in the final tree or resultant tree, we call as a penalty part. For better understanding, we can see, suppose it is a simple graph. and each vertex, there are 4 vertices, and each vertex is assigned with some price value. Along with that is edge or links also assigned with some weight. Okay. Now we have to find a tree such that the Steiner part plus, just like here, the Steiner part, then the penalty part, both combined one should be minimized. Okay. So one of the possibilities is, this is the tree where the total weight of connecting these 3 vertices and one vertex with price value 0 is excluded in the result. So the edges with red color, this is the solution, and total weight of this is 10, and its approximation factor, it is based on the optimum one we have calculated. Similarly, this is another one where the weight is 11. Here a vertex with price value 5 is excluded from the result or from the final solution. So here is another possibilities of doing that. Here no vertex is excluded, all vertices are connected, and total weight is 9. So this way some vertices will be included in the solution, some vertices will be excluded in the solution, and by doing this we have to do in such a way that the total weight of the edges that connect the vertices plus the set of vertices which are not included should be minimum. Set of vertices means the price value of those vertices which are not included. And basically one of the difference from the previous definition of the normal Steiner tree is that in the normal Steiner tree, specific set of vertices are given to the user. Okay, these vertices are to be connected, need to be connected. But in price collecting Steiner tree, we do not know which vertices will be in the resultant tree and which vertices will be excluded. That is not known prior to the execution or prior to the solution. Okay. Okay, so regarding that also we started this problem. Actually, we, to the best of our knowledge, we proposed the first distributed algorithm for computing PCST. We're not going to discuss details about that. I hope the problem, what is the problem, what is the Steiner tree problem, and what is its a generalized version, which is the price collecting Steiner tree problem, is I think clear to the audience. And now I am moving to discuss some of the use cases, okay, in the current trends of 5G, 6G cellular network. So 5G is an improved version of 4G LTE, okay, and we have to basically know about why the 5G is different from the 4G, what are the technologies, but mainly due to the increased frequency range. Mainly there are 2 frequency ranges in 5G cellular networks. One is frequency range 1, which was more or less same with the 4G network, that is the frequency range 400 megahertz to 7 gigahertz approximately. So this range was also in the 4G network. But here, new addition in 5G network is the frequency range that we call frequency range 2, as per the TGPP, okay, third generation partnership project for 5G. So it is also we call as a millimeter wave, where the frequency range is from 24 gigahertz to 71 gigahertz, and because of that we can connect millions of devices within very small geographical areas. Okay. And while the 5G operates, it operates in 3 frequency ranges, band. One is low band, mid band, high band. So this specification is there, you can see. Also the max speed that can be achieved in 5G is 1 gigabits per second. That's also known to us. Okay, what are the possibilities of enhancement in 5G network? This is important. So we should first of all know this. So the TZPP has proposed these three areas where enhancement of the capacity of 5G is possible. One area is enhanced mobile broadband. Of course, we can make it faster, which will give the higher throughput, which will cover more number of nodes, more number of devices. The second one is that is called enhanced mobile broadband, EMBB. The second area of enhancement in 5G network is ultra reliable low latency communication. So this is also one of the very important areas where in a very emergency situation where we need to change a very critical data without any interruptions, without any delay. In those situations, this area is very, very important. So ultra reliable low latency communication is very, very important. So basically our work is going to focus on this ultra reliable low latency communications where the Steiner tree will play a major role in improving the latency. Okay, we will see that some of the use cases. And another area of enhancement is massive machine type communications, where say a large number of devices, it may be IoT devices, need to be connected, then we will go for this. Okay, so one area where we can now see empirically as well as the theoretically also is the telesurgery and robotic surgery. So in the telesurgery or robotic surgery, of course, the patient is in some location. The doctors are in some other geographical locations, and similarly other associated components will be dispersed in different geographical locations. And yes, due to the ultra low reliable low latency provided, if it can be provided by the 5G, and if we incubate some technology by say incorporating some first algorithm like stereo tree, and also the data, the components, the nodes, means nodes here means we used to say that the robot, the doctors, and other components, they are spread it over different geographical locations, but each of them can be considered as a terminus. And we can connect with a very reliable network, which will achieve a very low latency so that there will be no distortion, there will be no delay in communications. So this is one of the area where we can directly fit our distributed Steiner tree, and there is a high probability of achieving the goal, means the operation can be performed successfully using this technique. So connecting all those components, we can directly use Steiner tree. So this is one of the use case where we can apply. Okay, for just informations for the audience, that first such telesurgery was done, we call it as a transatlantic surgeries. It was done in September 2001. The operation is called Lynchburg operation. Actually, the doctors were at New York City, patients were at France, and they successfully performed the operations of a patients in 2001. Okay, so another area where our Steiner tree can be incorporated is that because energy giving an energy efficient 5G networks, okay, because any network nodes where 24 hours has to be run, always the power hungry, and minimization of the power is one of the major objectives of any network, okay. And at the same time, we want to achieve the maximum bit rates. So this is one of the areas. So here, how we can formulate such network where we have to achieve an energy efficient 5G network. How we have to formulate? Okay, we will consider that tower, the network users, the devices, maybe IoT devices, all will be a node, and each node will be assigned some price value. Okay, for example, a node which is providing energy, but there is no user to use, we may lower down the price value or some value. The nodes which is heavily loaded, many users are connected and they are using it, we can give more value to that. So similarly, each user, each device, each node can be considered, and each node can be assigned with some price value. So this way, nodes are with prices, and a distance value by connecting from one user to another user, or one device to another device, or one cell tower to another cell tower in 5G, you can consider that as a distance value, that is the cost. So if this is the case, then we can formulate that problem for finding the minimum power and maximizing the bit rates as a distributed price collecting externality. We can formulate the problem as a price collecting externality, and if we solve that situation, the solution to that problem, the price collecting externality will provide minimum power, maximizing the bit rates. So this is another area of research. That's what we are believing, and we have also started with our students of exploring this area for finding energy efficient network in both theoretical as well as empirical way. We are trying. Okay, how much time left? Okay, another 5 minutes. Okay, this is a very because it is a current trend of machine learning. So we have also started investigating of this area, especially in machine learning. But since we are working on distributed settings, so basically that is one of the way of solving problem in machine learning is federated learning. Okay, in conventional way of machine learning is what data actually approaches the machine learning model in a trained in a central setting or in one phase, one machine. But whereas in federated learning, each node have its own data, individual data, and model is given to each node. The ML model is given to each node. Now they collectively, each node executes. They train their local data on the given model. Then the model parameters which they have found is sent to some central server. All nodes will do that, but they will not share the data, but only the model parameters will be sent. Now the server, which is collecting all the model parameters, they aggregates. Again, they update the model. Again, they send the updated model to the different users or different devices. And this way, certain rounds of you can say distributed rounds is executed until they reach some threshold value, like that. So this is what the federated learning. Federated learning in basically in ML is what they collectively find a good model. They collectively find a good model in machine learning. Okay, there are some different types of federated learning also. Client-server model, where there is a master, there is a server which controls aggregates of the findings, and again they requested the users. Then decentralized is like this graph, where this is more or less it's our domain of working, where we do not consider that there exists any server, client-server kind of model. We usually assume that it is a peer-to-peer model in distributed setting. Peer-to-peer model means that each node can act as a client, also act as a server. And of course, they are holding their local data. Data is not shared due to the privacy issues nowadays. This is also known to all. So data is local. They train on their local data. They just share the model parameters among the nodes. Okay, so this is our area of work. So we call it the decentralized federated learning. So in decentralized federated learning also, one of the challenges is communication and computation challenge. Okay, we have to minimize the number of communication, as well as also we want the minimum number of computation to get a good model in machine learning. So now this also can be formulated as a Steiner tree problem. Okay, basically this can be formulated as a price collecting Steiner tree problem, where suppose some nodes here, some nodes, any nodes, they are not performing well. That means their findings about the model based on their local data is not improving over the set of runs. So then such a node itself can declare that it's not no longer going to be helpful for finding an overall good model, so it can itself deactivate from participating in the finding a good model. And for that, each node, based on their amount of data or based on some other parameters, we can assign some price value. Each node will be assigned with some price value based on either the quality of data or quality of computation or the say, quality of the processors. And accordingly, we can assign some price values. And since price values are there and those devices are connected by a network like 5G, because we can utilize the advantages of 5G and we can connect them. And after connection, if the whole network can be formulated as a price collecting Steiner tree, and if we find a solution, this will give you a network which will produce a good machine learning model by using minimum number of communication as well as minimum amount of computation. So that is what our goal is. This is another area, not just machine learning. We also incorporate the graph-based solution to find the best model out of it. That is what one of the goal of our research. Okay, there is another predictive learning that is heterogeneous. Means the devices connected to network are not same, as we know. Some mobile phone, someone is a car, say someone is using a small phone, etc. So heterogeneous devices can be connected in 5G, and in heterogeneous situation also, based on the quality of the device, we can assign some prices, how much they can contribute to the network, and accordingly we can formulate it as a price collecting Steiner tree. Okay, that's what we have already discussed, that the collaboration of price collecting Steiner tree, federated learning, we can achieve ultra low latency model. We can achieve a machine learning model with minimum number of communication, with minimum number of rounds. That's what our goal is. Okay. For example, here is one instance where we have shown that it is a graph, and here V1, V2, Vt all are devices of different types, maybe heterogeneous, may not be the same. And accordingly some price values are assigned, and finally we got one tree with a dark black edges. So this is a forest actually. So this is a root vertex, and it is a rooted price collecting study. We can say, okay, those are some formalities we can learn offline, no issue. But what we are saying that during that process, some vertices like V1, V2, V5, based on some parameters, okay, that is the findings actually. That has to be found. Similarly, V7 and V11, they are not going to connect directly to the rooted tree. So we can discard this subtree or set of vertices. We can also discard V7, V11, V1, V2, V5. So this is a part of the price collecting Steiner tree. This is the penalty part. Where the penalty part? V1, V2, V5, V7, V11. The other set of vertices we call as a Steiner part. This is how we can formulate the problem associated with 5G, associated with the real-time use cases. Yeah. So this is what, in a nutshell, of I hope some glimpse of theoretical aspects as well as practical aspects of research can be found out of this talk. And if you have, from the audience side, if you have any query, you can ask me. I hope I have finished on time. And yeah, questions please.
So I would like to request from the audience, if they have any question, they can ask directly. They can talk with the professor also, and also they can type in their chat box also.
Hello, sir.
Hello. Good evening.
Good evening, sir. I am Arindam from Teshwar University. So
Okay.
I have a doubt. If we have many user equipments from different users, and we are routing our signal through each of them, then how are we ensuring the security for them?
Yes. This is one of the practical challenges actually. How we will ensure the data security. Okay. As of now, basically, from the theoretical aspects, when we solve a problem, we always assume that data is secure. When basically in a distributed setting, we solve the problem either in a message passing way or shared memory way. So our proposed algorithm is based on message passing model, where we assume that data is secure during the passing from one node to another, or one processor, one device to another device. But ensuring data, this is also a different topic of cryptography, definitely. That is our assumption. We have not taken care of how data is secure from device to device. Yeah, this is also another field of exploration as per my understanding.
Okay, sir. So correct me if I'm wrong, sir. Is this tree solving the problem of, like, since it's a very high energy wave, it gets destroyed. It can travel longer routes. So we have to either, instead of this method, we have to install many base stations, right? So is it solving that problem also? So we can reduce the cost of installing base stations, and directly we can use those user equipments.
Yes. This is what our objective is actually. This is our objective. If we actually at the very beginning, when the network came, just like say laying down the fiber optics cable as well as connecting them to the towers. So basically, it is nothing but it is a price collecting scenario actually. Whether you will install a tower and connect the tower, or you will not install a tower at any particular city. If it is say millions of cities or thousands of cities, then just by doing manual, it is not possible. So if we fit, because here a city, it is a node, it is a cell tower, and we know that how many customers we are going to get, and based on that, the revenue will be generated. Revenue will be the price, and some idealistic condition we used to think, and that's how company actually used to formulate it. Each city tower, they used to consider, okay, price value, whether now they are going to connect or not by laying down some network equipments. So laying down or installing network equipment itself is a cost that can be formulated as an average, and the tower value, the revenue generated by a tower, from a tower or from a city, so that is the price. So this will give you a better solution, definitely, the more profitable network to the company.
Okay, sir. Thank you.
Okay. Yeah, is there any questions? You feel free to ask, and if you any drawbacks or any disadvantage in our discussion also, you please don't hesitate. Feel free to share with us.
Is there anyone? Sir, I'd like to ask a simple question regarding those 5G, 6G, and the distributed things and the graph theory. Regarding the implementation, like while doing the research works regarding those graph theoretical problems, so how you used to do, like you used to set up the physical things, or like it is a simulation and emulation based?
Yeah, there is a two group of doing actually attacking any problem. We say they're attacking any problem. One is to validate the problem by using empirical way, okay, based on simulation we use to say. And another way is establish your facts or findings theoretically. Basically, till today itself, I can say what the problems I am tackling or I am taking to solve is by giving the theoretical solution, means proving the theorem, the facts are established by theoretically. And since once you establish theoretically, no need to validate by using empirical data. But since theoretically it is established, but to apply in real situations, definitely we have to do it in an empirical way. By collecting data, we have formed a physical network and we have to validate. So from the research point of view, academic research point of view, it is perfectly fine if you can establish theoretically by giving the facts, you analyze properly and produce the facts. And also there is another way, you establish, since theoretically may not be feasible sometimes, so you establish the facts, like most of the machine learning so proposed models, algorithms, they're based on what? The accuracy, all these things. Those are actually not, in terms of approximation, not accurate. So accuracy is done not 100%, maybe 90%, 80%. So yes, both way is correct, both way is acceptable, but only point is that we have to target a correct value. But because if you have done some theoretical work and if you target simulation-based conference or journals, they may reject, and vice versa. The both way is valid, and since I have done and many of us in the theoretical foundation, they are also doing. Yes.
Okay, thank you, sir. Oh yeah, there is a question in the chat box. Rivale Shaha has asked the question.
Okay. Yes, I can see the questions. He has asked, as the optimization problem of finding the minimum Steiner tree in a network is NP hard, will it be challenging to find the optimal Steiner tree in large scale 5G, 6G networks with numerous nodes and connections? Also, 5G, 6G networks are expected to operate in a dynamic environments with changing traffic patterns, user mobility, network conditions. Will static optimization techniques like Steiner tree handle it? Yes, very good questions. Actually, this is also another part of research. Yes, actually, this problem is because the real world problems are not static, it is dynamic, and nodes are heterogeneous, connections are also going in and out. Yes, so there is another variation of Steiner tree called dynamic Steiner tree. Okay, so regarding that, dynamic Steiner tree will be able to handle such kind of situations to some extent, but static are not going to work on it. Yes, our work is a very rare, it's a idealistic assumptions we have done. The network is static, nodes and links do not fail, and nodes are also cooperating. It's not like that they are hiding some data. They are cooperating each other. Those assumptions we have done, and based on those assumptions, actually, we have worked on. But reality, to come to the real ground, yes, dynamic Steiner tree is more realistic. I hope it is clear to some extent. It makes sense to you. Thank you, Lilia Saha, for this nice question.
Thank you, sir. Do you have any paper on this, that we can follow to get a more deep understanding into this dynamic Steiner tree?
Yes, I have a paper. Just the problem we have discussed today, the Steiner tree, distributed Steiner tree, definitely is the static one. So it is it was published in 2021 and Journal of Parallel and Distributed Computing. You can find it. Yes, we have. Also, the preliminary version of this work actually was published in ICDCN conference.
Okay, thank you, sir.
Yes. Also, actually, also we have also work on the recently we have work on say it's related to the Steiner problem that is called traveling salesman problem. It's a very well known, more than 400 years old problem. We also tried to give a distributed version of it recently. We are also working on it, more or less similar to Steiner tree. Of course, it is a theoretical stuff. Okay, getting paper in theoretical is I personally feel it's very challenging because very less people nowadays are working on theoretical foundations. But still, there are people who appreciate it. Yeah.
Thank you, sir.
Thank you very much.
So I'd like to ask, is there anyone who wants to ask any questions to the speaker? I think probably there is no one having any doubts. So I'd like to thank Dr. Parikshit Saikia for the wonderful talk. It is a very very interesting, and also I'm also personally working in the networking domain, especially in the software-defined networks and the IoT part. So it's very interesting. So again, related to the 5G and 6G, there's 5G has already been started, and 6G, I don't know, I think maybe after 5 years or 10 years, it may start. So I'd like to ask, what do you think about the in the data center, the application of 5G or 6G in the data centers? Will it be applicable in case of 5G and 6G in the data centers, wireless servers and all?
Basically, by 2025, as per the research, most of the data will be will be sent to the edge server. We call it the edge server. So data center usually we call it a cloud. It is a cloud. The cloud and edge a little bit different. So that is what just like federated learning is doing nowadays. So most of the data will be transferred to the edge server. Okay. So if this is the case, then definitely the 5G and 6G will be greatly helpful. Connecting all devices, giving equal importance to each of the devices. They can use the bandwidth, the enhanced bandwidth in 5G and 6G. Yes. So exactly what was the question? Question is that is the data center are going to use the 5G or 6G heavily or not? What is the question?
Yes, means the deployment of 5G, 6G in the data centers, the wireless servers actually. As per my knowledge, everything is in the Ethernet and that kind of communication only.
Data center will be always there, but at the same time, as nowadays it is shifted to the edge server. So edge server and data cloud is of course not the same. So since of course 5G and 6G will be helpful for data centers, that means those data centers will be converted to the edge servers in future. Of course, more than 75% of the data will be processed in the edge servers only. So 5G, 6G, only because of 5G and 6G, because of that, it is now reality.
Yes, definitely. Okay, thank you, sir.
Yeah,
so, I'd like
just,
to yes, sir. Yes, sir.
Yeah, just I would like to thanks once again for giving this opportunity. Okay, it's also a nice experience for me.
Yes,
this is the second talk actually I gave as a formal second talk, and yeah, it's a great learning for me also. It's not just a talk; it is also a learning. And thank you very much for your whole team. Thank you.
Okay. So before the ending, I like to request each and everyone, if they wants to we will have a photo session. So if they wants to turn on their camera, they can turn on their camera. We'll take some screenshots. Then there will be a small token of appreciation. Then we will conclude the meeting. So I'd like to request my teammates to take a screenshot, and I'd like to request everyone if they can turn on their camera.
Yeah, one of my BTech students is also present. Nice to see Kedarnath. Pawan, yeah, right. Arindan
I
is also here.
I know one from NIT Silchar. I think you know Vishal Talukdar.
Vishal Talukdar, yeah, somehow I have heard his name. He is working in his.
In the CSC department only. BTech. He's from.
Oh, he is BTech, okay.
Yes.
Oh, okay. Vishal, I know one student. He is also in my hostel. I am the warden of one of the hostels.
Okay, sir.
So maybe he might be.
Okay. Sir.
Yeah, Sivani also there.